So I can't delete the parts where I mess up completely. You all have to just put up with that. Um, Everyone will see the bloopers. Okay, so I'm going to assume that at 10 minutes after the starting time, we have who can show up and that other people have had things happen. I know things happen. Right before this meeting, we had a branch that was like 8 inches, literally this big around, fall from 90 feet up in a tree and land on our roof and come bouncing off. Everybody went running outside to see what happened. This branch that's 35 feet long landed on our roof and bounced off. The whole house shook. So everybody has things going on these days. In my slide set, why don't I see if I can figure out how to share that real quickly. Share that screen, screen 3. Boom. Share. Oh wow, everything on my screen immediately jumps around. Yikes. Did I do that to everyone else too?
Yeah.
Okay, well, there we go. I'm back to good. So what's supposed to happen now is something to bring us all together and make us a group with a shared purpose. And so I know you all are here. So those of you who could turn video on did. I really appreciate that. What we're here for today is to talk about how computers work on the inside, sort of what the logic is and what the physicalness of them are, and figure that out. Linda had suggested an idea for how we get started that I kind of like. What do you think if we broke into small groups? Who here has been on a Zoom call before, actually? Just put your hand up so I can see if you've been on a Zoom call before. Some. So there's a thing called a shared whiteboard where we can draw pictures together. I think, who's good at explaining the shared whiteboard? Jeremy, are you good at explaining the shared whiteboard?
So one person shares their screen and it's just a blank screen, and then they can annotate with either a marker or with stamps or with text, and other people can also annotate.
So in order to annotate, what do you have to do? And I have to figure out how to unshare my screen, I think.
You have to, no, you can keep going. So you have to do view options and then annotate above exit full screen. And then, just for example, I could do these stamps everyone can see.
And how do you do those stamps? How do you get to those stamps?
Well, you click view options in the top
Oh,
middle.
okay, view options at the top. Mm-hmm.
And then stamp is the fourth thing from the left.
And apparently when you share your secondary screen, it doesn't let you stop sharing. Do you all see my slideshow but not maximized now?
Do you want me to put up a whiteboard, Rob?
Yeah, I think a whiteboard. I was trying to do that, but I can't figure out how to stop sharing my desktop. I've never done it on a second screen before, apparently.
Yeah, okay.
Can we kill my shared screen? Here, maybe here.
I can't get it back, so.
I just found stop share. There we go. It's on a totally different screen. I'm good now. Okay, I stopped sharing, right? So now we could share. I'm sorry for the delay. Now we could share whiteboard if I can figure out how to do that. There we go. Share, whiteboard, share. There's the whiteboard. I think I have to do this the more traditional way. Okay. So do you all see that I can draw here? That's shared with everyone. Who else can draw on that? Can you draw on it? Because we may want to share some drawings as we go today. And I guess I'm most interested in who can't quite draw on it, and can we help them learn to draw? If you can't draw on it yet, put something in the chat and we'll see what we can do to help that work for you. It looks like a lot of people are drawing. All right. If you have not managed to draw something on the whiteboard, will you, I guess, physically put your hand up or put a question up from using the emoji stuff you can do? So, Archie, you're having trouble drawing on it? Oh, because your brother's got it? Who can't draw? Is everybody drawing now? All right, I'm going to go with everybody can draw now, except for...
can't draw. Wait, like 3 people can't. Not working.
Okay. So what's happening, and can someone help Archie and Malcolm draw? So up at the top, there should be a place where you can say that you want to annotate. If you go up near the top, there'll be a thing that drops down. And it'll let you grab a pen and draw on the whiteboard. Okay, you can turn your sound on so we know, so you can ask questions. So Archie and Malcolm, are you drawing now? I can't tell.
Yeah. Yep.
Okay, perfect. Okay, we're going to assume everybody can draw, and I'm going to stop this whiteboard. I should save it. It's beautiful. There we go. Okay, all right, we're going to move on with what we're actually doing today then. We have quite a mix of people here. We have people from Chris there, who spent his whole life in technology, to me, to people who are just starting programming. So we're going to start at the beginning a little bit and then move on. Let's see how this goes. I have a slideshow. Let's see if I can share it and we can use it. We're just going to start really basic if I can figure out how to do this. Here we go. Share. The first question is just computers. Do we all agree on what computers are? Wow, it's so silent. Everybody is so muted. I don't know if I can work with you all muted. I think I'd rather have background noise. What do you guys think?
Can see.
Let's try it. Let's try it. Unmute. Let's see how bad it is. I'm much better with real people. Let's say something.
Hi.
Oh, it's almost like you're here now.
We can see you. Yeah, I mean, we can hear you.
I'm glad you can hear me. I need to hear you just a little to know you're really there. Hi. Hi, Brendan. Okay. So, and I know, Sophia, you don't have a choice about this. I feel really bad about that. But okay, so let's see what we can do then. Computers. Who has an idea of what a computer is? What's your idea of a computer? Somebody tell me what their idea of a computer is. It's okay to speak up, really. It's okay just to make everybody else wait while you talk. I love it when people do that.
There's something that does some computing.
Okay. Yeah, good.
A smart device.
A device? Uh-huh.
Like a screen that you can type.
Okay. A screen you can type on? Cool. Is an Arduino a computer? An Arduino doesn't have a screen.
Yeah.
It doesn't have a keyboard. Is it a computer?
Well, it doesn't really computate.
Okay, it doesn't really computate. Okay.
Yeah, it's given a set of instructions and then it follows it.
Okay. How about, do any of you have one of those smart thermostats in your home? Like you go and you can set the air conditioning or the heat for your house?
Yeah.
Is that a computer?
Nope.
Yeah.
Oh,
No,
Well,
Okay.
it exhibits observation and reaction.
it is.
okay. I mean, this is really interesting. How about your cell phone? Is your cell phone a computer?
Yes.
Yep.
Okay,
Yeah.
everybody agrees a cell phone's a computer. This is good
Nowadays, it is.
nowadays. Okay. All right, well, so I heard some interesting commonalities. I heard something about you can put stuff in it. It's got a screen. Our phone doesn't have a keyboard, but it does have a screen on it, right? I'm going to propose a really special definition of a computer, and it's going to be a little different than what some of you think, maybe. If I can figure out how to move forward, here we go. Click, there. So are any of these parts absolutely required? Which of these parts could we throw away and we still have a computer? Do you see anything there that's...
Keyboard.
Wi-Fi.
Wi-Fi.
We don't have to have Wi-Fi, okay.
Display.
USB.
USB inputs.
Do you need input?
All right, so we don't have to have USB. What else? I heard some more. Keep going.
Keyboard.
Keyboards.
Okay, sometimes we don't have a keyboard.
Display is also
Display.
We don't always have a display. Okay. Which parts do we have to have? Which parts do you think that if we leave them out, it's not a computer?
Inputs and
Memory.
outputs.
Processor.
Okay.
Programs.
Memory.
Inputs and
Memory.
outputs.
All right. So inputs, outputs, memory, a processor. Cool.
Programs.
Kind of organized. You need all the stuff on the right on the left.
All right. Yeah. So you guys are getting to what I think of as a computer. I think of inputs and outputs, memory, and a processor. My background is I'm formally trained as a computer scientist and a software engineer. And it turns out we get trained in what a computer is. And one of the simplest computers, it can actually be made out of wood. I'm going to show it to you a little bit if I can figure out how to share it. And then we're going to look at one made out of Lego, okay? Because I really want to get down to what is a computer so we can talk about exactly that. So let me figure out how to share this. It's going to take just a minute.
This is interesting, Anika. Watch.
Is it an Alan Turing machine?
Now we can see another kid.
Oh look, it's a child.
Okay, I think I did this right this time. We're not going to watch this whole thing. This is actually an instructable. You can build your own Turing machine. A Turing machine is one of the simplest kinds of computers that anyone ever thought of long before we had electronics. This was something you could make with paper and a pencil. So I'm going to show you a wooden one that somebody made. I'm going to jump through it. It spends a lot of time showing you inside that. Then I want you to see it. Actually, can you see my cursor?
Yeah.
Yeah.
So do you see these little pegs on this wood?
Yeah.
That's memory. The peg can be long towards us, or it can be pushed away from us. And if it's pushed away from us, it's a 0. And if it's long towards us, it's a 1. That's memory, just like in our computers, 0s and 1s. That's what Turing invented, the idea of memory that's 0s and 1s that you could record in a special way. So now let's watch it. I want you to see the motion. And peg it. You see this part that goes up and down? When the stick sticks out, it gets blocked. And you see how far it goes down when the stick doesn't stick out? That's how it knows whether it's reading
Turn
a
off the
0
audio
or a 1. You see that? Sometimes it sees a 0. You see this part, this little wooden part down here? You see how it's making them long or short? There we go.
Much better.
Sorry, this one, yeah, we don't need the audio on this one. So this is a machine where it's manipulating memory. If you see up here, do you see this thing with the little metal pegs that you almost can't see in the picture?
Yeah.
That's actually the program. That tells it whether to push the pegs in or out. Every time it goes by, these little wooden things discover if there's a peg there or not. And that's where the instructions for the program are. So this is a person who's built a wooden computer. And they built these long before we had electronic computers. So let's look and see if it has everything you need. It has output. Oops, I went too far. My bad. It has output if you read the values of the little sticks that stick in and out. It has input in how you start those sticks, whether they're in or out. And it has a processor, which is this program up here, and then all of these mechanical things that manipulate the sticks. That's a pretty crazy computer, isn't it? And you know how complicated the program can be? It's really cool. It can compute things like 2 + 2 = 4. It can even say 4 + 3 = 7. That's about how complicated this program is. Can you imagine if you tried to make one with 4 gig of memory? That would be 4 billion of those little sticks. How many times would you have to turn that crank to do anything? But this is a computer. I'm going to say that this is a computer. So now we're going to move on. I'm going to show you someone else made a computer that I think is actually a little more fun. It has a modern day computer in it. Do you all agree that an EV3 is a computer?
Yeah.
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 That's too loud. So this is a computer. This is also exactly the same machine that we just saw, but it's running using an EV3. I'm going to let it show you. Hold on. Let's see if I can. There we go. It's very similar to the one we just looked at, except for it's run by an EV3. Do you see how instead of having sticks, it has toggles? And there's 2 + 2, and it's going to figure out an answer, which was, right now it's set to 0. I figure many of you have run EV3 machines before, so this might be something you recognize. So it had input. Remember, it showed us 2 + 2 = question mark. And here's where it's doing processing. It's reading each of these things with the camera and then moving them with the piece that moves. And when it's done, it'll have output. We'll be able to look at the memory and see what the output is. And look at that. The output is 4. I know that's really amazing. 2 + 2. You now know the answer. You've been waiting for this whole workshop to get there. Okay. Let's look at how computer scientists have made this formal. Wrong. Here we go. So the basic idea here, a guy named von Neumann came up with this really, really cool idea. First off, that all you need is some input, something that can do logic, and some memory, and an ability to have output. He came up with this really interesting idea, and I want this to be in your head because it's really important for modern day computers. So we had data in the, let's see, in the wooden machine. You remember we had a program that was little metal pegs? You can nod if you think you remember. I'll know you remember that there were little metal pegs. Yep, Archie's got it. And we had data on the strip of wooden pegs, right? They were wooden pegs that had data. What von Neumann came up with is he realized that the program is just another kind of data. Why can't you put the program down on the wooden pegs? Why do you have to have it up in the metal pegs? This was like a crazy, weird idea when he came up with it. Nobody thought that made sense. But all of our computers work that way. Our program lives right where our data lives. I'm echoing now. I think it's because I've turned on sharing of sound. Hold on. Let me share again. There we go. Should be out of. Am I sharing the same thing? Okay.
No.
No, I'm sharing my desktop now.
Yeah, the program thing.
There we go. Okay, I should be back and right this time. So the idea here is that you have input that goes in a processor. It finds the program in memory and it finds the data in memory. It does something with it and it creates an output. And we're going to figure out how that all happens, okay? Because that big black box of memory is kind of confusing. So a modern computer looks more like this. Who did we just have arrive? Oh, okay, I see. Anchor's coming back. Or a different anchor. No, a doubled anchor. In this model, we show that we have, this is the processing unit. This is your, if you had an old Pentium or one of the new Intel chips, the 3s, the 5s, the 7s, this is the processor. Over here is the memory. We have secondary memory. We'll talk about that in a minute. And then you have all these input and output things like printers and displays, your mouse, your keyboard. And this gray area, this is a way of connecting them all together. Those are the wires inside your computer that connect them all together. Okay? And what we're going to talk about today is mostly how the processor, how the processor and the main memory work together, and a little bit about secondary memory. Secondary memory is like your disk drive or your USB thumb. Any place you can store it, and when you turn the computer off, it still remembers. And this is going to be the kind of memory where your programs run that's really fast, but when you turn your computer off, it forgets everything. So if we take this model, what does it apply to? Is an EV3 brick a computer, do you think?
Yes.
All right. How about a Chromebook or a laptop?
Yes.
Yeah.
A cash register?
Nope.
No.
No.
Actually, yes.
I guess it depends,
Actually,
doesn't it? There are some cash registers that don't have a computer in them. They're purely mechanical. There's some cash registers that actually they have a keyboard where you type in numbers and they have a receipt that comes out and they run a program to figure out what the inventory is. And those might actually be a computer. What do you think?
Oh yeah, definitely.
A microwave oven?
Yeah.
Yes.
Nope.
Yeah.
I suspect most microwave ovens have a computer today. How about a car?
Yes.
Yeah.
Yeah.
Most cars today. An older car doesn't, but most cars. An Arduino, we're back to Arduino. We weren't sure about it before. Do we think it's a computer now?
Yeah.
Yeah.
What makes it a computer that we weren't sure about before? What do you think?
Like it gives an input and output, I think.
Yep, and it has a little memory and it can run a program of some kind. How about a Raspberry Pi?
No.
Yes.
Yeah, Raspberry Pi is almost the same as a Chromebook. In fact, you can
Oh,
make your own
I thought
Chromebook
they
using a
talked
Raspberry Pi. What else can you think of in the world that's a computer? That would surprise somebody who doesn't know as much as you know about computing. What's something different? I mean, a tree's not a computer.
People.
Yes, a person is a computer by this definition.
No.
It's just sort of a naturally occurring computer, but so is an ant and so is a dog. So I think we're talking about human-made computers. Do you agree?
Yeah. No, we have them all over the place.
Anybody have a watch that's digital?
Yes.
Yeah, I
Can
do.
you set your watch?
Calculator?
Can you set what time it is?
Yeah.
Can you
Yeah.
set an alarm?
Yep.
Yeah. Yes.
Can you read what time it is?
Yes.
Sounds like a computer. Okay.
Well, wouldn't by that definition an analog clock with the mechanical mechanisms for determining time?
I think it's a mechanical computer, depending on how well it can interact with memory and how variably you can program it.
That's true. It doesn't really have memory. It just has a mechanical output.
Right.
Oh yeah, the door locks. Some door locks.
Some door locks are computers, right? Right. So the Turing machine was a mechanical computer, but it had mechanical memory, right? Memory that could change state, not just run from here to there, which is different from your mechanical alarm clock. Okay. So good. Let's just write some code. You all see this code on the screen, right?
Yeah.
Really easy. Anybody could write that. I mean, we now know we got memory and we got a processor. What's left? I mean, I'm done, right? You guys feel really good? I taught you lots. Nobody's quite feeling that way. All the faces look really worried that that's where we're going to go. We're not. This is not where we stop. So this is assembly language, which is a text representation of machine code. This is sort of what the computer does inside. It says load 6 into the processor in position A. It says load the thing at this address into the register named HL. Load whatever's in HL into B. Oh my gosh. Does that sound like a program to you? I mean, it might, but it's complicated, not very easy. So the hard thing about this is you have to come up with a plan for what's going to happen and what's going to go where in memory. It's like inventing that wooden machine. You have to think of all the bits of it that make it work. And that's complicated and hard, and other people are going to have thought of good ways to use memory. Here you have to decide how are you going to use each piece of memory all by yourself. And that's really, lots of engineers did that and decided it was too hard. So they stopped doing it. So here, instead of using that insane code, has anyone used any of these languages before?
Yes. Yes.
Which ones have you used?
UV3.
EV3.
C,
CV3. Scratch.
Yeah. Just
Cool.
C and
I heard someone
Very
say
little
C.
bash.
JavaScript.
Cool. JavaScript. All right, so I've been doing software for a while, so the secret here is that when we get to when we get to the one that says M4, starting with Rust, those are languages I haven't used before. All the others I've had to use. So if you go into computer science, you may learn a lot of languages. The cool thing is once you've learned a couple of them, they get really easy to learn the next ones. But that's just a small portion of all the languages in the world. Why do we have so many, do you think? Anybody got a theory why we have so many different languages?
proprietary software.
Some of it's proprietary. Any other ideas?
Like Scratch, it's like drag and drop, so it's like easier than say Python.
Okay, it's sure different. And for some people, I believe it's really easier, and for others, I think, like I'm somebody who finds Scratch much harder than Python. Okay, so what do they have in common? They're all pretty different. Scratch is pretty different from Python. Do you agree?
Yes.
So what they have in common is, for the most part, they all agree on how to use memory. All that memory the processor can use, all those little twigs that can go in or out in the wooden model, you have to have a plan for how you use them and what they mean. And almost all of those languages agree. The two languages that don't agree that were in that list, here, let's go back to that list. COBOL and Fortran are so old that they don't agree. They use memory differently from all the others. But all the others pretty much use memory the same way. And that's handy because if you know how one of them uses memory, then it turns out you know how all of them use memory. So that's like a real lever. You say, gosh, I might need to learn 10 languages, and then you find out that mostly they all do the same thing in some way. So let's see how that works. So this is memory. This is that string of wooden things, or the Lego toggles. It's just a bunch of numbers. And the numbers aren't really numbers. The numbers are just a way to tell us that certain positions in memory are turned on and off. And we decide that that means a number. So whenever we talk about memory, we have an address. You see this column here? We say the 0th position in memory, the 1st position in memory, the 2nd position in memory. And depending on the computer, there may be 8 yeses and nos. There may be 64 yeses and nos. I've picked one here where we have 64 yeses and nos. We have quite a bit here. I think I did 64. Yeah. And I just wrote it out as numbers, and I actually generated those with a random number generator, so they don't mean anything at all. In case you think those numbers mean something, only the addresses mean anything. But the processor has to say, I want the numbers at a special place, and so the address helps them do that. And depending on which computer processor we're using, the address may tell us where, if it were a house, you all live in a house or an apartment, and in your house, a certain number of people live. How many people live in your house?
3.
3?
3, 5,
6.
Right. So the number in each house is different. So in one computer, we put the same number of bits in every house in any given computer. Different computers agree on different numbers of people that can live in the house. For people, I'm just using that to represent a bit at an address. So let's move on. This looks complicated. This was designed by an engineer, and engineers love to make drawings, and they love to make drawings with fancy words in them.
Oh, yeah.
Okay? It's not very complicated. When you find out what this drawing means, there are 2 things that are going to have happened. One is you're going to know something they usually don't teach you till your 3rd year in college, and the other is you're probably going to laugh at how it's not very complicated. It's really not very complicated. And this is your 3rd year in college if you're studying computer science. So what is all this? This is a plan for using memory. Here's memory. It's just numbers. Here's a plan for what you're going to use those numbers for. Really quickly, let's just look at it. Down here where it says text, text just means your program. It actually means your program, the code you wrote. Data, who's made a variable in a program? Let me know if you've made a variable. What'd you name it?
I have a bunch of different ones.
Okay.
I mean, like, it was EV3, so we didn't name it or anything.
Okay, did you give it a value? Did it start with a number value when it first started? Or did it get its value from a sensor or something? Did you tell it the first number it was going to use?
Yeah.
I think.
Okay, so when you tell it the first number it's going to use, that number gets stored here in initialized data. That's all that means. This data segment is a place where you put all the numbers from your program. That's all it is a place to put numbers that you told the computer about. This uninitialized data, did you ever have a variable that you didn't tell it the number and you let it read a sensor? A line follower where you didn't tell it if it was light or dark, it just was light or dark based on the sensor. Did you ever do that?
Yeah.
I had a code thing that had user input.
Okay, so in all those cases, all of those variables go here because that way they just wait to find out what their value is. That's not too complicated. And then we're going to talk about heap and stack in a minute. They're interesting. And that's what we're going to spend a lot of time on as we talk today, is about heap and stack. But really, that's it. That's the entire thing. That's the plan. You've got a program that's instructions. you've got data that you told it about, you've got a place to store data you didn't tell it about, and you've got a place for your program to run. That's the whole thing. It sure looked more complicated than that, didn't it? I think Miranda's laughing, but she's silent, so we don't know this. Now, can anybody tell me what's going on here?
It's an abstract view of order of operations.
Anybody else tell me what's going on here? No? Okay.
Oh, no.
Upside down.
It's
It's
upside
upside down. It's upside down. So one of the things that happens is different companies that built computers disagreed about things that didn't matter very much. And so some of them put addresses in reverse order. Some of them put the bits at an address in reverse order. Computers just are built differently. I like my stacks to go up. But you notice the people who drew this have their stack going down. It's okay, it doesn't matter. I just put this in here to remind you that different computer manufacturers build their computers different ways. It doesn't change what we have to know about the computer. What's important is that your program starts at 0. And we don't care if 0 is at the top or at the bottom. Look, here I put 0 at the bottom, and we count up into memory. See how we're counting up into memory? And in the other one, we were counting down into memory? Okay, that's funnier if you had to live through it. So we're back to normal. We're right side up again. We've already talked about this. Basically, the computer memory is like the toggles or on the EV3 Turing machine. We have this simple memory plan where we have a program, we have data for the program, we have space to put the data, and we have heap and stack. Here's where the computer program actually decides. When you write your program, it says the number of instructions in your program, your EV3 drawing or your Python text, take this many bytes to be stored. So it picks an amount of bytes and it says they start at 0. And then it says how much data, how many variables did you tell them what their value was at the beginning of the program? And it picks the right amount of memory and it basically draws a box around it and names it data. And then it says how many variables do you have that you need to store stuff in that maybe don't have data in them? And it makes a space for that. And then heap. Let's talk about heap now. Sometimes in a program, what if you had a program that stored the names of people who walked into the forge? Okay? You know we have a program like that, right? So you have a program like that. How many people are going to walk into the forge today? Do you know ahead of time? Well, yes, today you do. 0. I'm sorry, on a normal day a year ago, did you know how many people would walk into the forge in a day? Or how many people would be on this call?
Somewhere between 1 and 100 or 200, depending on if there was an event.
Sure. So we could have a list that's 500 people long and only put the right number in it. And that would work, wouldn't it? What if we really didn't know? What if some days 1,000 people came and we could only store 500? Our program would break, wouldn't it? So some data we can put here in this blank stuff because we know we're only going to store up to 500. But if we don't know how many, then we stick it over in this heap. This heap is some extra memory we can use for things where we don't know how many of them there'll be. And we have as much heap as the computer will let us use. It's literally a heap of memory. You know why it's called a heap? Because it's a heap of memory. That's exactly why it's a heap. And that's just extra memory. And do you see it has a big arrow here? That means if we need more memory, as long as your computer has more memory in it, we'll just keep using up memory. Now over here, we have the stack. And in a minute, I'm going to show you exactly how the stack gets used. What's important here is that the stack also grows depending on your program. And there's a problem here. Can you see what the problem might be? Who can guess what the problem is if the heap can grow in one direction and the stack grows in the other and they grow towards each other? What do you think happens? Can anybody see a problem coming?
Like overlap or like collision?
Yeah, they collide. It's called a collision. And when it happens, it's really, really bad because what goes in the stack is your running program, the parts of your program while they're running, and what goes in the heap is the data it's using. And if you start putting parts of your program in your data and start putting parts of your data in your program, then you start executing your data, and your data usually isn't a very good program. That's really bad. And that used to happen a lot in DOS. In Windows and Linux, we now have some protection against it, but it used to happen really badly. And it can still happen on an Arduino. So, okay, let's move on.
I have a question.
Yeah.
So if you have more RAM, would you avoid the collision?
You do until you don't have enough RAM. More RAM makes the collision less likely. It's always good. And there are certain ways you can write your program so the stack grows slower or the heap grows slower, and those are really good ways to avoid the collision. But you can write a program that will collide. If you write a program just right, the stack will grow no matter what you do. You might say just wrong. And if you do that, the stack grows faster than you can add memory, and they're going to collide. I think Mariah Hunter wrote one of those in school, maybe, because of the way she's grinning.
Not with that intention.
Oh, well, yeah, nobody ever does it with that intention. Okay, so what's really important? Why do we do all this? It's like sections in a library. Memory is just this random place we can get lost in. And when we're writing a program, we don't want to get lost. Getting lost is sort of the opposite of what we want with a program. So we need to know where the code lives, where the data lives, where we store things that we're reading and writing to. We need to know where we have extra storage, and we need to know where our program has room to move its elbows around and not bump into anything. That's really important. So by having a plan, we make sure things go the way we want them to and not the way they go. Mariah Hunter was laughing because she wrote one that accidentally didn't follow the map, and that goes really badly. Has anyone else written one that didn't follow the map and discovered that yet? Have any of the rest of you done that? I mean, that's the thing that you don't all, Scratch protects you from it pretty well. Has anyone else written one where it didn't follow the map and it crashed really badly? Has anyone ever seen a blue screen of death?
Oh yeah, I've seen plenty of blue screens of death.
Anybody else?
I mean, my computer does that for other stuff, but like not programming.
Okay.
It's
So a blue
sort
screen
of
of death.
like when you have an EV3 program or a line follower, and you have the set of instructions it's supposed to do. It isn't the same, but it's sort of, and you tell it to turn left, and it randomly goes in different directions, never the same one, and it just keeps doing that. It's not like that. That's more of a bug in the program, but it just unexpectedly keeps doing things, and then it dies. You can't fix it.
Right. If that happens on EV3, then under the covers, this is what happened. It stopped following the map.
Mm-hmm.
So, and every time you see a blue screen of death, you can be pretty sure that something didn't follow the map. Do you know what the most common thing that happens that causes it not to follow the map? Can I show you? You may have run into it already. If you notice that our code always starts at 0, the text segment is always at 0.
Yeah.
If you ever try and reach out and use data that's at 0 or try and run code that's at 0, it yells at you and crashes because it knows that if you're trying to change your program from within your program, that's a bad idea. You shouldn't be rewriting your code inside your code. And it knows that the code lives at 0. So if you start writing your data into 0, it says, wait a minute, you're writing your data onto your program. And so almost every modern computer actually crashes rather than letting you do that. Hello? I heard a noise, sorry. So let's move on. So here's your map. You know you have it. It's easy to get lost. If you put the right thing in the right place, it's easy not to get lost. The computer doesn't care. That's for us. Okay, now we're going to start looking at some programs. Hold on a moment. I'm going to have to change what screen I'm sharing. And start sharing a different one. Hold on just a moment.
Any questions while this transition's happening?
No.
That didn't go right. We'll fix it. Okay. So here can you all see that?
That's such an organized desktop.
It's because it's my extra desktop.
And we had a question as well.
Oh yeah, I want to hear the question, please.
So one time I downloaded, well, the Windows update I downloaded had a bug in it.
Mm-hmm.
So every so often when I started up my laptop, it didn't have a blue screen, but instead it had a green one, and it had the same text as a blue screen, like the weird frown face, and it just said Windows stop code error, but no, it just fixed itself 10 seconds later.
Huh. So mature operating systems, and Windows is getting there, often have a backup plan for when things go wrong. And we can talk about, after we get the basics down, we can talk about how they do that, what the processor does so that you have something smart to do when something bad happens. And so let's walk through how this code gets mapped into memory. And then let's talk about what happens if we put a bug in the code and what the processor can do about it. Okay.
Should we be seeing code at the moment? Because
can you see?
Yeah, we still have your desktop.
Oh, well, that's not helpful. Let me try again. Share. Oh, I clicked on the wrong. There we go.
This looks a little more codey.
And
okay.
I'm wondering how many of our people here have coded only in visual languages versus coded in text-based languages. How many people have coded mostly with Scratch and EV3 compared to... A helpful thing here before we jump into code?
I think it's going to be okay because my plan is to talk about the equivalents in Scratch and EV3. And I'm hoping that our EV3 and Scratch people will be expert enough in their languages to help me do that. I'm going to need some help. I have done a little bit of EV3 and a little bit of Scratch, and so I think we can get there. But if you haven't yet done a text language, you especially should ask questions, because your questions are going to help all the people who are too afraid to ask a question, who think they should know because they've done text languages. And you've got the advantage of, you can just say, I've never done a text language, so you got to explain it to me. Okay? Because we need that. I've used text languages so long that I'm going to assume things that I shouldn't assume. So this is a C language. It could be Java. It could be Python. It could be JavaScript. I chose C because the mapping of C to hardware is probably the simplest mapping after assembly language. It's easy to read the code and know where things are going to go. It's a little harder to do that in Python and Java. But once you've seen this, we can talk about how it would happen in Python and Java. We can talk about how it would happen in Scratch and how it would happen in EV3. Okay? You brave? We're going to go. We're going to try this crazy. Who here has actually done C? I'm going to guess we only have 2 people who've done C. We got Brendan.
Oh.
Anybody else?
I did like one line, and that's it.
Okay, so Mariah Hunter. Who else? One more.
I did like one line. And
Chris, okay.
It's like Hello World.
That's a great program. That tells Hello World does everything we're going to do today, practically.
And
okay.
I did too.
Monica, I did C2.
Okay, so we got about 4 people. So we've got some help from me. That's good.
5.
5. Cool. All right, so I'm just going to walk through the program one line at a time. First, we're going to do it to see what the program does. We're just going to start at the top and move down to see what happens. And then we're going to look at it from the point of view of what happens in the computer. The first one is what happens if you're a human. You're just a programmer. What does this program do? And then how does the compiler and the loader put it in the computer so the computer can actually do it? So what do we have here? We start with this line. Why do we start with this line? This is, sorry, again?
Nothing. Never mind. Sorry.
No, I think you were right. So this line gets a standard input output. The IO is for input output. And it says that somebody else has already written code that can read and write from the keyboard and to the screen. And it saves us from writing that code. So we don't care about that very much for today. We do care about this. Look, we have a variable, a place to put a number, and we have a number we're going to put in it. That's pretty important. This says we have an integer named magic quit number, and the number is 17. I don't know why we have that yet. We have to read the program, but we have a magic quit number. We're going to ignore this for a minute, okay? We're going to have a simpler version of it, and we're going to come back to it. All it says is this is the main part of the program. This is where the program starts, okay? We can look at it in more detail later, but it's complicated, and I'd like you to have a better background before we do the complicated part. By the end of today, you all should actually be able to say, I understand this, which will be really cool, but I don't think you're quite there yet. So now we have a variable called quit, and it's type Boolean. Who can tell me about Boolean? What does Boolean mean? Does anybody know?
Just looked it up.
False.
True, false.
True, false. Okay. So right, it means this variable can remember true or false, and we're telling it to remember false. Do you all agree?
Yep.
Right here we say, I actually read this sign that says equals, I read it as get. I say quit gets false, meaning put the value false in quit. And then we have a number. Do you see we have a number here? What value is it? What number do you think we put in it? We haven't put a value in it.
No. Yeah.
At the moment, it's a random accidental number, and it'll be different every time we run the program. So we better not use it for anything like it is, because it won't be predictable. But it won't really be a random number either. It'll be a question of what program ran in the computer before. We'll figure out why that is. Now what we're going to do is, while quit is equal to false, we're going to increase the number of guesses. Oh, I'm sorry, we had a number of guesses, another thing that has no value in it. We're going to say the number of guesses gets 1 bigger. It looks like we're going to get a number from the user. We're going to print the number they guessed. And then if that number equals, oh, the program is written wrong. Hold on. I was smarter than this. Magic quit number. If they guess the right number, then we're going to set the Boolean variable quit to true. And when we come back up here to do this again, because this is a loop, we're going to find out that quit is not equal to false. And so we're going to print the number of guesses, and we're going to quit the program. So this whole program is this silly program. All it does is you run the program, and it asks you for a number. You type the number in, and if it likes your number, it quits. And if it doesn't like your number, it makes you guess again, over and over and over. Can you imagine that program?
Yeah.
Is everybody pretty comfortable? This is one that makes you guess until you finally guess 17. And once you know that, you can get out of the program really quickly. But otherwise, there are a lot of numbers to guess at, aren't there? And then it prints out how many times you had to guess and quits. Let's look at just that much and how that lays out on our map of the computer. Can we do that?
Yeah.
You guys ready? So now what we need is our map of the computer. Look, that's my email. This is where I want to be. No, that's not where I want to be. Here. That's not where I want to be. Here. Here we go. I don't want to be full screen. Okay. So here's our map of memory. And here is our program. So our program gets turned into numbers. Do you agree that our program has to get turned into numbers the computer can run someday?
Yeah.
Yes.
Boy, this is getting long and boring, I can tell. We got to make this work better. Hold on. So we got it turned into numbers, and we're going to stick all those numbers here in the text section. That's where your program lives, your code, right?
Yeah.
So we're going to run a compiler or Perl or something, and it's going to turn it into numbers. And then it's got some other things. This magic quick number, where is it going to live? Where are we going to put it?
The data.
Right. So here's what's going to happen. Let's add 17 is going to go into our data somewhere. And the other thing that's going to happen is that space for magic quit number is going to go into our storage space for information. We're going to create a space that can hold a 17 and put it there. So I realized when I explained it to you, I wasn't very clear on that, but that's what's going to happen. We're going to put a space in our blank stuff place, and we're going to put the number 17 in our data stuff. And when the program starts, it's going to copy the 17 from our data to our space. How about this one, number of guesses? It's going to create space for number of guesses and put that in our area for blank stuff. So it turns out that magic quit number and number of guesses might both go in our blank stuff. And then when the program starts up, it's going to grab the 17 out of the data and put it in the magic quit number space. Everybody's so silent, and I can't tell. I immediately am sure everybody's very worried when you're all so silent. Help me out.
Ground noise.
I need to know you're really there. I'll freeze up. I need your help. I need as many people of you as you can not to be muted, or I'll freeze up.
Hi.
Hi, thank you. Now I just know that there are real people out there. That's important.
It's nice to pass that Turing test.
So thanks for helping me. Okay, so interestingly, when we get down here to quit is not going to go into our blank data or at all. It isn't going to go in here. False is. False is going to go into our data, and the program's going to remember that that belongs on quit. Number isn't going to go in our blank data, so they've got to go somewhere. Anybody have any idea where they could go? Heap? Okay, good. Heap is a great answer. It's not the right one, but it's a great one. I really like it. Where else could they go?
Stack.
There's also the stack.
Stack. And they are actually going to go in the stack. So what's going to happen is when your program gets turned into something that can be put in the computer, every time you start with a function or a method or a my block, or what are they called in Scratch? They're called my blocks in EV3. What do you call a piece of code in Scratch that you can separate out?
I don't know.
Yeah, I'm not sure Scratch has that. I mean, I know it does underneath, but I'm not sure as a person you can tell Scratch. Well, so you can. Certain blocks take a number, right? You give a number to a block.
Yeah, there are numbers that take in different feedback.
Different, right. So that block is in fact a function then. If you can give a number to a block, the block is a function. So main is our first function. So what's going to happen is we're going to go to the stack. Oops. And we're going to do this. First off, over here, we need a processor. Do we have a processor? We don't yet, do we? Do you guys see a processor in our drawing yet?
Yes, no.
Okay. So if we don't have a processor, we're missing some things. Because what we're going to do is we're going to put instructions over here in the code. Each instruction is one thing the computer can do. And we need to know where we are right now. So we need a processor. And our processor has to be able to remember the current instruction address, the current value that it got out of memory, and where to go next. Does that make sense that you want to know where to go next? What instruction to run next?
Yeah, that'll help.
Might. So these are some of the things it has to remember. It actually remembers a whole lot more. But we start the code at main, which is right here near 0. And we're running through the code that says create quit, create number, test if quit is false, right? We're going to have all those instructions over here. And so we're going to start at instruction 1, which might be create quit, go to instruction 2, which might be create number, and then we're going to go to test to see if we should quit yet, and then we should go to increase the number of guesses count. All of those instructions are there. And at some point, we're going to get to this line. This line is really weird. This line says, go run some code over here at get number from user.
Yeah.
Right now, who's completely confused? I need to know. I know some people are confused. I need to hear who's confused.
I'm confused, but I'm not sure by what.
Who else is confused? You don't have to know why you're confused. Who's confused?
I'm confused.
Confused.
Okay, cool. That's helpful. Let's break this down a little and make it a little easier. Let's go right here. Oops. And let's imagine we have a program. Let's take just a few lines from our program. Let's take just that many lines. I'm hoping this will paste and not be silly.
Wasn't super silly.
It's amazingly not silly, actually. Surely there's a way to change the vertical spacing. Oh, well, it's good enough. Okay, so there we have some code. And it comes from our big program, right?
Mm-hmm.
So over here, we're going to have a box of memory. And it's going to have addresses. Actually, we need 2 boxes of memory. 1 box of memory, but 2 different boxes. Okay, and at position 0, we're going to say put false in the variable quit. Do you agree that that's sort of what that line means? Does that make sense to you, that that line might mean do that, and that there might be some numbers we could put in memory that grab the value false from one place in memory and put it in another place in memory?
Yes.
So what would happen when that line ran is it would say the line would be up here, and it would go up into this section, and it would find the 17 because it knows the address of the 17, and it would put it in the quit number down here, which is the, oh no, sorry, that.
Yeah, you got that a little backwards.
Right, I did, hold on. This is just the local quit. This isn't the quit number. This is just the local quit. We just have a quit, and we're going to put false in it. So where does that quit live? That's what we need to know, is where does quit live? Right, the global one would work just like I said. Let's do that. Let's make it easy. Sorry, let's do this. So here's the global one before main. And it would say magic quit number.
What's a global variable?
Perfect question. Thank you. Put 17 in the magic quit number. So that's exactly what we're going to do right now, is what's the difference between a global and a not global variable? Good question. Thank you. See if I can get this to work. Sorry, and I'm going to answer your question, but I need this to be on one line. There we go. Okay. So any variable that lives in the in this section, in our blank stuff section, is global, and I'm about to tell you why. And any variable that lives in the stack is not global, and I'm about to tell you why. Okay, that is a great question. The reason is that this section of data, it is always there, and we don't change it how it's organized. We only change what values we put in it. But where the variables live in it, when we put in magic quit number in here, we put it in one place and it's always there. When we put number of guesses in there, we put it in one place and it's always there. So any part of the program, it's anywhere in the world you live, you can know that the number of guesses is stored in that one place, and you can go get it. You can go get the current number of guesses. You can change the current number of guesses. Anyone, anywhere in the program, any part of the program can change it. Okay? It's sort of like a secret cache we put in a park, and anyone can go in and write a new message in it, and everyone knows where it is, so you never know what message is stored in it, but you always know it's the message that is in the secret cache box. So that's a global variable. What's that?
It only fits one message.
Right, one message, and that message is always at that place, and everyone can access that message. So it's global because the whole program can access it. A local variable is going to be over here in the stack. And I'm about to show you that the stack changes all the time. And so if you don't know what's on the stack right at this moment, then you don't know anything about the stack. And if you try and use a variable that's on the stack, you may get in real trouble if you don't know enough to know when you can use it. So we're going to look at that right now, okay? Good question. That's a fabulous question. Have I answered about half of it? Are you okay that I've answered half of it? That you now know where the globals live and why they're global?
Yeah.
Yeah.
Okay. Now the locals, they're going to be harder. In my mind, global is sort of like my kitchen pantry. Sally, my wife, likes to reorganize the kitchen pantry. She's doing it right now, in fact. And when I go back and I expect to find the spaghetti on the top shelf, it isn't going to be on the top shelf anymore. And I'm going to have to look everywhere. And if I reach for the top shelf, I may end up with candy, or I may end up with a mouse trap. I don't think we have any mice traps, but mouse traps. But I don't know what's where. It gets reorganized every time I'm not in there. And that's really important. The stack is like that pantry that gets reorganized all the time. Do any of you all have a shelf like that, or a pantry, or maybe a part of your bedroom that a parent cleans up and then you don't know where anything is?
Yeah.
So that's what a stack is like. It changes all the time. So let's look at how it changes. So for the global, we had a thing that said put 17 in the address where magic quit number is supposed to be stored. And the way that worked is it knew 17 was up here at a certain place, and it knew magic quit number was down here. So it grabbed 17 and put it in magic quit number, right? It grabbed the spaghetti and put it where the spaghetti belonged. That easy. The program knew how to do that. Now, quit isn't global, so it's more complicated. We're going to have an instruction here before we ever go into main that says build stack frame or main. And that's actually a really complicated instruction. It's probably 100 different instructions all at once, but we're going to pretend like it's one just to make life easy for us, okay? So what's it going to do? It's going to go to the stack. Do we have room for a stack here? And the stack is a bunch of addresses. And the first thing it's going to do is say, I see we need room for a quit variable. So it's going to say room for quit, size of a Boolean. However many bits you need for a Boolean. How many bits do you think you need for a Boolean?
2.
1.
1. Absolutely. 1 is exactly the right number. Now, I'm also going to tell you that unless you have 8 Booleans, no one does it that way because the addresses are interpreted 8 and 64. So they waste an entire address even if you only have 1 Boolean. And only if you're doing really special stuff do they optimize that. But you only need 1 bit, and you waste the other bit. So room for variable quit, the size of a Boolean. So it's going to, I don't think I spelled Boolean right.
Nope.
So it's going to make sure that on the stack, let's have a stack here.
Spelling the vein of my coding existence.
What is?
Spelling.
Oh, yes.
Yeah. Mine's capitalization.
I try to avoid capitalization because I know that it will trip me up.
Yeah.
Cool. So it has 1 byte saved for quit. The next thing we see is, oh, and then it's going to have an instruction. Let's move it. The next instruction is going to be put false in
बेटा तू ध्यान दे रही है उधर?
Quit. What's that?
Sure, Rob.
So now false is in the space for quit. And then it's going to say make room for an integer named number.
वो 8 इसको जवाब क्यों?
What's that? Oh, it's background noise. Okay. We don't know what goes in it yet. It's just whatever happens to be in memory there. What if the last thing you ran was a spell check? Then maybe it's got the letters from the misspelled word sitting there on the stack. Maybe the last thing you ran computed pi to 592 digits and it's got the 487th digit in it. You don't know what's in there. It's just some number based on what used to be on this computer, because you didn't have, there's no instruction that says set it to anything. Now we have number of guesses. We have a test. We're done setting up the stack frame. Almost done setting up the stack frame.
Yeah.
There's one last thing we need. We need space let's have 4 bytes space to remember where we were. In a minute, you're going to see that's really important. But for the moment, we're just going to say space to remember where we were. Okay? It's a way of kind of, I seem to have a cat climbing on my chair.
Yes, you do.
I think he wants me to let him out, but I'm going to hope someone else will take care of that. Apollo, say hi to everybody. Okay, we'll see what happens. If he gets impatient, he'll climb all over my keyboard, and then we're in trouble. Okay. So let's try and go through our code. We know we have a place where quit is. We have a place where number is. We're going to test to see if quit equals false. Where would we get false from? How do we know what false is?
Was a fifth bit in your stack.
We know that quit is in fact false, right? We can see that we stored false in quit. And we know what false is. The program knows false is equal to 0. When we run it, it knows false is 0. That's sort of defined in our program. So, cool. Then so we test that and we find out we can run this because quit is equal to false. So we're going to do number of guesses. All right, where the heck is number of guesses? We're the program. We're trying to figure out what to do. Does anybody know where number of guesses is? All right, Brendan, you've been answering. Anybody else know where number of guesses is? It's okay if you don't, because this is what it's all confusing. Anybody know? All right, let's go find out. This is why we have a map. Number of guesses is in our blank stuff place. Whoops. Do you see that number of guesses is in our blank stuff place?
Mm-hmm.
Yeah? Sydney, you okay that number of guesses got hidden in our blank stuff place? You can nod, it's okay. Can you see that? How about you, Arjun? Do you see that we decided number of guesses would hide in our blank stuff place? So our program has a map that remembers where everything is, okay? And it remembers that that's where number of guesses is. So down here, we say, let's add 1 to whatever is stored in number of guesses. Now here's a really important question. What is currently stored in number of guesses? Anybody have a guess as what's the stored in number of guesses?
0.
The number of guesses.
We want the number of guesses. How many guesses have we made before we run the program?
9.
Oh, 0.
0. So a secret thing the computer does is, remember when it put somewhere in our program over here, we had number of guesses. And remember when we went through the map, we put number of guesses here? The computer sets all of these things to 0, all of them. And then any of them that had a number stored up here, like 17 or false, it copies that to where it belongs. So Brendan was right. It actually is set to 0. The computer does that at the beginning of the program. It takes care of that magic for us. So now what's stored in number of guesses is going to be 1. 0 plus 1 is 1. We're going to put 1 up here in this data place in our storage, and it'll never get zeroed out again unless we tell it to get zeroed out. So every time we go around in that loop, that number will get bigger. Have you ever written code in EV3 or in Python where a number just gets bigger and bigger because you keep adding to it?
Mm-hmm.
Yeah? Anybody else?
But mostly you try to make it so it doesn't get bigger for infinity.
Right. This one only gets bigger till you guess right.
Right.
If you keep guessing wrong, is there a potential that it could collide?
This program is written so that it won't collide, and I'll show you how that works in a minute, okay? Because that's a really good question. You could write this program so that it would collide, and I'll show you how to do that because it's kind of fun. You should write one like that and let it collide and watch it crash. It's very exciting to watch it crash, and it's a good way to learn. So now we know the number of guesses. We've said they're going to guess. We're assuming they're going to guess. Oh, and we're running out of time. It is 5 o'clock.
Oh, wow.
Wow. You all are either really interested or really bored at this point. I need a vote. Which one is it? Really interested or really bored? It's okay if it's bored. This is the first time I've ever done this. How are we doing? Uh-oh, Brendan's got us like this. He's not sure. That's all right. Good answer, Brendan.
Confused, but also intrigued.
How about everyone else? Are you feeling like this is a good use of time? Would you come back another time and finish this? Or is this like, oh my God, I can't believe someone asked me to sit in front of this and I so don't want to be here, but don't tell anybody. I'm okay. You can say that. What do you think? Help me out. Okay, we got another maybe. A bunch of maybes.
Yeah, I mean, I find the information very interesting, and it's actually helping my mind wrap around what I've actually been doing with the microcontrollers and stuff.
All right. So what I want to do is get where we can connect it to Python, and I feel like I maybe wasn't as prepared as I could have been for you guys. I probably should have done a smaller beta and gotten this a little more prepared. I think he's saying that's exactly right. Is that what that means?
Yeah, sign language. Yeah.
Wow, because we didn't quite get to where the big payoff is. I hate that, but it is 5 o'clock, and I want to respect everybody's time. And also, if they really feel a need to get off because they're bored out of their minds, I want to give them a chance to do that too. Sydney, am I hitting the button there? It's okay. No.
So what's the most interesting thing that people have learned from this? And what's something you want to know more about? Can we find out what people liked and didn't like, since this is a beta and that's part of the goal, is how to make it better?
Yeah.
So
learning about the code.
Learning about the code was good?
Yeah.
And what was the most confusing or challenging part?
The stack kind.
Right. We're just getting to the stack, and yep. And I bet that's the most confusing part.
All right, let's see. Krithik's next on my screen. Oh, wait. Arjun.
I just talk.
Yeah, Arjun's next. Sorry, going through my screen order.
So I still have some questions, like how would the program not collide? But one thing that I did learn was how computer, like, I didn't know about all of the stack heap and all of that, but I don't want to know, but I also want to know what happens if I try to collide a program.
All right.
I can send you a program that'll collide if you want.
I'll pass.
No, I'll send you the text of the program. Not that you have to run it, but the text so you can see how to make it collide. But we really need to do what I'd hope to do in the next 20 minutes is the part that would show you what collides. And we just, it's 5 o'clock already and we didn't quite get there. It took longer than I thought to get this far.
All right. Unker is the next one. I'm not sure if I'm saying your name right.
Oh, no, it's fine. It's actually my dad's name.
Ah.
So I liked learning about the heap and the stack. But what I would like to learn, I could probably do this by myself, but like the probabilities of like what types of computers would collide. Like I remember you guys saying that like an EV3 would collide, but then also like a normal laptop would also collide, but like the probability of that happening would be really cool.
Ooh, interesting.
So if we can make, if we come back together another time and do the very next part, the part we didn't get to, then you'll know enough to know how to figure out that probability. Because you can make that probability 0 or you can make it very high depending on how you write your program.
Do we have anybody on Alicia's camera? Any Archie or? Looks like we've got empty chairs. We can jump to Sydney.
Oh no, there's a hand.
No, there's a hand. What did you find interesting or confusing? Both of those. Oh, do we not have a mic over there?
We got a hand shrug.
Got it.
Archie, is that Archie? Oh, let's hear your voice. So there, you're not muted. Was there one thing that was interesting, Archie?
I don't know.
Okay. Was there one thing that was so confusing that you don't ever want to hear about it again?
Okay.
Okay.
All right, and then we have Sophia's mic is broken. So if we could get it in chat, that would be awesome. All right, Nikhil. Oh wait, no, Sydney's first, and then Nikhil. What did you guys?
I thought the heap and stacks thing was both interesting and a little confusing.
Definitely. All right, Nikhil, what did you find interesting and what did you find confusing?
I got to learn what an address and the global variable and the local variable was, and I'm a little confused on the stacks.
So we're definitely getting some stat confusion. Okay. RN Uma? Anything from you or Usha?
Hi. Yeah, I find it really interesting because it's new and little bit we are not at there to completely understand. That's why probably we are a little confused at this stage. So when we come back, and I know Rob can walk through to the end, then we will find it exciting. Right now, yes, the initial part was really interesting about how the different parts of the program as such processing and thing. So I feel like we are in the middle. That's why there's confusion not. But when we go to the end, we may be happy. So I would like to come back.
Great. All right, and Badresh?
So I would want to come back, and I found the stacks kind of confusing, but like I learned the parts like of the computers and programs and stuff.
Okay, and Brendan, anything to add? Confusing, most interesting?
Well, I drew a picture, and it's really cool to see kind of the stack and heap thing. I just started programming about a month ago, so it's all pretty new to me, and it's good to see a little bit of the physics behind the magic. Something to give me something to grasp onto rather than just relying on it doing what it does.
Yeah, nice to have the little short sketch of where everything goes to refer back to. Did I miss anybody? Tried not to, but as people unmuted, people moved around.
So I want to thank you all for giving me a chance to try this. I have a much better idea of how to do it so that it holds together a little better next time. You all were really patient with it not all quite holding together. I'm not surprised that the stack is confusing right now, because we barely started, and I should have given you a model of what a stack is before we started doing the details, and I didn't do that. What do you all think? Should we do this again next week at this time? And I have a whole week to get ready, so I'll have some actually really good drawings instead of just things we're doing at the end. And we'll see if we could actually make it so that you all say, oh, stacks. Ha! That's so easy. I get stacks. Because I think all of you, based on your questions and what you've done, if I explained it well, I think everyone who was here could understand a stack. I think the only reason you don't understand it now is I didn't explain it very well. I explained the first part really well, and I hadn't realized quite how hard it was going to be to explain a stack. And I think if you get stacks, you're going to love them. To me, they are one of the most inventive, cool things that humans have come up with in programming. But that's up to you. So do you want to try next week? Should we just try doing this, pick it back up? Yeah.
Bob, if you stop screen sharing, then we can see all the reactions.
Good. Let me figure out how to do that. Hold on a sec. Stop. I'm sorry. I could see everybody. I'm sorry that it was harder for you. So yeah, what do you think? Should we go ahead and do next week? I've got a couple. That's a yes. Okay.
Okay, so at least, yeah, that's somewhere over half, 3/4 of the people have given it a thumbs up.
So let's do this at the same time next week, and I'll send out a Zoom link. I'm going to share the slides from today, and I'm going to add some to the slides to make it a little clearer where it wasn't as clear. And then I'll have a set for next week where we can really pay attention to the stack, because I think, again, once you get the stack, you're going to love it. It means you own the computer. If you understand the stack, you own the computer. You really do. You own what your program's doing, and I want you to be able to do that. So I'll send out an invite so that you can decide you want to come or not. And we'll start next week with like how a stack really works. Not a confusing description. Well, it might be confusing, but not too confusing a description of how a stack works. All right? Does anybody have anything they want to say before we go off, either in text or in voice?
Thank you for doing this.
Thank you, Rob. Yes, thank you for doing this.
Rob.
That was great, Rob.
Thank you.
Yeah.
It was really fun. I hope it can be more fun next time. I'm learning too, just like you are. I mean, that's the thing. We're all learning as hard as we can. So have a good weekend.
Yeah,
write a program between now and then in any language you like, even if it just says hello world.
For sure.
Maybe next week we can tear your program into memory. Show how it goes into memory using a stack. All right. Thank you very much. I think we have to call it done.
Thanks, Linda.
Thank you.
Thanks for sticking around to give feedback for an extra few minutes. See you all next week.
Bye, everybody.